I've made the front panel. Okay, I've cut it, rounded off here. I've marked where the hole's going to be, and now I'm just gonna mark first where the hole's going to be on there, and that's the same size there, and then I'll drill it with a smaller size and I'll tap the holes. So just a marker here only. Okay, so now I got the small marks where I will drill and tap. And now let's see. That hole looks good. Sorry, that hole looks good. Does that hole look good or not? Yep, it's alright. Focus. Yeah, not bad. Okay, and now I'll tap it. I tapped the rest, I'll just show this one. I sprayed a bit of WD-40. It actually helps a lot with soft aluminium. This is very soft aluminium. If you don't, it seems to gall the aluminium if you don't put any oil. Unfortunately, on the other ones, I didn't put the oil and they didn't come that good on the threading. In actual fact, I have one here on the side. The thread's not good. See, that went in much better with the oil. Ah, shit. Okay, thank God I didn't break the tip. Okay, that's it. I countersunk the holes, and I'll just try the screws now. See how we go. One screw. Second. Okay, this seems to be fine. Last one. This one. Okay, you can see a defect here. This one is slightly out. That's that bracket. It's slightly longer this way. The way to fix that is to make a new bracket, but you know, that's why I said it's got a few defects. But anyway, that's the face, and now it's a matter of working out where I'm going to have the holes for the adjustments, display, and the output, and this main switch. That's the box there. back. Okay, still more things to go. Okay, so regarding the fans, that's how they're gonna go. So I made a bracket there and a bracket there. One fan will fit like that, and on the back, bracket there and a bracket there, and another fan will fit like that. Will fit on there, the same as that, but at the back. Now regarding the cover, okay, the panel here. Okay, I decided, bring this down. I decided to just drill holes. So what I'm going to do here, I've made a template on the computer, and I'll be just drilling these holes for the fan, and the same as that for the front fan. Okay, so I've got markers here. I will put a little punch hole, and I'm just going to drill it like that. So I'm not going to be cutting a big hole and fitting something like that. This of course will let more air in and more air out, but I'll probably drill these holes slightly bigger than what they're drawn on there. Yeah, I'll see how I go with that. When I think about it, probably I do not really need all the holes in the square. Just realized now. I probably can draw a circle there, and it's no point drilling other holes that are not part of the circular, so I might delete some of the holes. Anyway, that's that. Okay, just to show that what I did, I marked all the where the holes with a little center punch, and then I went with a small drill as a pilot. That's what I drilled these ones, and now I'm going to go with the bigger one, final one, and it's all by hand. I cannot fit this in the drill press. It's too small, my drill press, so unfortunately it's all by hand. So that's how it's done. Not perfect, but it's all I can do. Okay, so I'll carry on. Okay, so there it is. That's one fan hole. You can see the fan fits in there. It's actually came pretty flush with the case. Okay, and that's the back one. I'm going to have a handle here. It's set a bit back because the transformer is back, so when you lift it, it will be more balanced in your hands. So the circuit board here, I have installed 3 standoffs plastic. So I'll just take it off for you. It's all about setting up where all the mounts going to be, all the components, and the heat sink. Okay, and I put a little support as well here, a bracket. I got some insulation there. It's not for the electrical part on the bracket, mainly so if the transformer gets warm and warms up the case, it's not picking up any heat type of thing. It's not a tight fit, so it just fits on there. So this heatsink's got a groove here channel. It's from an old computer, old PC power supply, I think, that heatsink. And I've got the 3 standoff screws here, plastic, so it's insulated. Unfortunately, this circuit board it's a very bad design regarding mounting screws. I don't like how it's only mounted there, no support here, and that's why I thought I'll put a support there, so it's supported also there, so it's not gonna twist on this section, because from that point to that point there's no support. And those holes, that's not for support, that's the actual connectors for the triac output and input. So the transformer is going to be mounted there, just got to bolt it. So I've got the screws ready to go. This transformer is mounted. I drilled the hole for this power connector. I'm going to have to put a fuse here. Still have to drill that. So still amazing how many little bits and pieces you have to do. So I'll just remove this. Okay. Also, I put 4 legs, mounting legs, whatever you call them. Okay. And the bottom. So it's higher than the screws and all that. Okay. And this is just a bit of insulation here, just in case under here where the 240 volts is blows up or anything, you know, we don't get any more too much shorts to the ground. But this box needs to be earthed, so we'll have to have a good earth. And so yeah, I gotta put a fuse and still have to make the front screen. So at the moment, that's all I'm up to. Okay. The front panel, I've drilled the holes. I've made a template on the computer. I've already marked it, drilled it. These are for the display, holes for the switches. So I'm just gonna, this is how I do it, and I'll use the jigsaw, and I'll cut over here. All right, something like that. Anyway, that's how it's done. Okay. And once cut roughly with the jigsaw, then I use the file to get the right size. So I'll be doing that, just filing away. Okay, so I've done that. The most difficult part is cutting the square hole for the main switch, circuit breaker, and the display. Okay, continuing on with the spot welder. I have made a template here. I think I have said that before, I'm not sure, because I took a bit of a break of it. The only downside, of course, well, one of the downside of this circuit board, this Chinese spot welder circuit board here is that it only goes to 1 to 50 cycles. Some people on the internet they think that's 1 to 50 milliseconds, but that's not correct. So each cycle, if your power at home is 50 hertz, each cycle is 20 milliseconds. Okay, so it will go from 20 to 1000 milliseconds, which means you can spot weld maximum of 1 second. Okay, if you're running in the US or in Europe, places where they use 60 hertz, then it's 16 milliseconds is the minimum, and the maximum will be 833 milliseconds. Now that's fine for doing, from what I can understand, because I haven't done it yet, spot welding batteries, terminals. Okay, but if you want to use this spot welder to spot weld metal, you might want 2 seconds. Okay, so this thing doesn't do 2 seconds. It only does 1 second maximum here under the 50 hertz. So that's one downside of that. From what I can assume, they probably would have done that, so this triac here will not blow up, okay, or the circuit board, because it's limited. Now the other thing that I did on the circuit board here is I added a varistor, okay, parallel with the triac, and it's always good to do that for the high voltage spikes. So that's the 415 volt varistor. Correction, the varistor I use is 430 volts. Okay. Now the wiring, I will make a circuit diagram for this to show. The way I've done it is just a quick explanation. I've ran 2 fuses. One fuse is for the control circuit, which will only be about 100 milliamp fuse. Okay, and the main fuse I put a 12 amp, which is heaps, but because only I'm using a 10 amp circuit breaker here on the front panel. Okay, otherwise you probably put 10 amps fuse here. Now again, on my testing, I was able to draw 1000 amps on the secondary, but that would have taken around 12 to 13 amps on the input. Okay, so I'm switching on the switch, which everything is temporary, the neutral for safety as well, and the active. Okay, so the power comes in at the back, it goes straight to the switch, it turns on to these bottom terminals. So one will supply the neutral, and I've connected a neutral connector here to be able to supply the neutral to the transformer here and to this transformer. Okay, and the active, or the live, which is this white wire, goes to the fuse terminal, to the main. It loops to the control fuse. The output from the control fuse feeds the transformer, and the output of the main power, which is this one, the 12 or 10 amp fuse, will feed the circuit breaker, okay, and the front panel, and then from the circuit breaker it goes to the circuit board. So I'll just disconnect the circuit board here, and then from the circuit board, which is this wire here, goes to the transformer. Now still a bit more work to do. As I said here, I connected a varistor. I've put it in the terminals where you can fit a 100 amp triac in there. At this stage, I'm not using the 100 amp triac, so I don't think I need it. And the wires input, I've built it up with solder here directed at triac. So if any case this blows up, I don't want to be blowing up the tracks. Okay. So just an extra solder there. And I've used silicon wires. These are all from equipment that I chucked out. Anything that's still good quality, like silicon type of wire, high temperature, I keep, and that's what I've used these wires from. Because if you had to go and buy these, it cost you a lot of money, you know. The other thing I did, the potentiometers, which were soldered here, I removed them and I put these plugs here. I just bent the pins and put these circuit board pins here and soldered it to that. So I can, the front panel, when I connect the pots, it's a matter of plugging them in. I like to have things in that way for the reason if I want to take the front panel off, I can I'll just unplug everything, okay? The transformer side, you can see that's how the terminals are, like that, okay? That's how they are. And so I'll be honest with you, this I probably, as I said before, if I was using this spot welder to do other things, I mean, in the future I might, I don't know, maybe to, you know, spot weld 2 pieces of metal. This is not going to be good enough because it hasn't got enough time. 1 second won't be enough. So this is an ST C Chinese microcontroller. I never programmed these, but I'm interested to see if I could put my own program in there and just change it, because I actually think these LEDs here, which are all pretty much outputs of the microcontroller, are pretty useless. Maybe one is still okay, just to tell you that it shows when the trigger is on the output to the driver here, to the triac. But they should have made, for example, instead of putting an LED there, having like an output, or instead of you connect the LED, you connect a fan or a trigger for a fan. So that's why I've put the fans, just in case in the future I will modify the program or have my own circuit board that I can have longer time. Now, how this triac, even this is a 40 amp triac, or the 100 amp, let's say if you're welding for 2 seconds or 3 seconds at one go, okay, at, let's say, you know, high current, 12 amps or 10 amps on the triac, I don't know how that would survive. But if I find, for example, that it will be blowing up, because I know that these could blow up even at not that much current. If this cannot survive, then you would use 2 SCRs back to back, you know, at high current, similar to what I used on my Variac. And that should make this thing bulletproof if you're welding real high currents. Okay. And what I mean with the SCR back to back, it's one of these units. If you're going to have this, you know, spot welding for, you know, 2, 3 seconds, 4 seconds, even longer, you'll just install one of these. Okay, so what I have in front of me is the NY D01 circuit board, just over here. And that's the display for it. I've got the potentiometers here. We'll change the cycles, change the power. And then over here, I have the same chip that is used in this board. And as I said, I might try to do is to change the software on board on the chip here to be able to have my own software, and that's what I'm doing. So at the moment, the software is only a trial. I don't know how it's going to perform exactly, but I've got an oscilloscope hooked up to it, and I wanted to change it because this cycles only goes from 1 cycle to 50 cycles, and the 50, that's the power there. So the power also starts from 30, that's the minimum, to 99%. Okay, now what I did work out is that the power is not, the indication of the percentage is not a true RMS reference. So whatever this is saying, if it's 50%, you would expect to be 50%, 90 degrees, being a phase delay control circuit. You would get 90 degrees, which is 50%. It will be actually 5 milliseconds delay after zero crossing, okay? So what I found was that it is not set up like that. It's obviously, I think they have done this for maybe 2 different reasons. One is to have the pot to have better control from 30 to 99, okay, not to be flickering around. And also is they probably worked out that certain percentage is not going to do much for your work. So I think they've set it up like that. But I have not set mine like that. So the software that I'm doing, I'm going to be having mine here, which will go from, sorry, that's the cycles, where in mine is in milliseconds there. The power will go from 1%, okay, over here on the LCD screen. So that's the same chip that's running there, and I'm running an LCD screen. And also it actually runs this at the same time. And I will show you that when I unplug that and plug it into my board. So the power here, mine goes from 1% to 99%. And my percentage is worked out exactly true RMS power delivery from the sine wave, okay? Now the power is going to the actual true power on your weld is going to depend on your transformer. It's going to depend on the cable size used on the transformer, and many various other things. You know, your spot weld points that go onto the job. That will alter the current, so the power will change. But I would like to know exactly what the wave is being referenced at, okay, corresponding with a true sine wave, true RMS power delivery. So my one is set exactly correct to true RMS. But I wanted to increase my time to 2 seconds. So my one goes from 0 cycles to 99 cycles. And as you can see, 20 milliseconds is the lowest, which is 1 cycle at 50 hertz. Here on the LCD screen, 20. And when I turn the pot, over here I'm turning the pot, okay, I can go, so that's half a second. That is 1 second there, okay. 1000 milliseconds, and the max range is 1.98 seconds. Okay, but I wanted that just in case in the future I want to weld like two thick pieces of metal together, and so you would need longer time to be able to melt that and to heat it up. Regardless of what the try can handle it or not, I don't know because I haven't tried it. But also, I want to show you here. This is the chart that I've made. Also, I used the AI on Google to create the true RMS power. What would that would be equals in milliseconds in percentage of true RMS power to milliseconds, and of course there's the formulas there. A bit too complicated to explain. I'm not a someone good with that. So what I did here, this is what I've set my one goes to, from minimum is 1% to 99. Of course, the table here is only jumping at 5%. Yes, don't worry about the first two here, 1 and 2. I've put them for a reason. I'll explain that. But it's jumping by 5, 10, 15, 20 and all that. But of course, the percentage control is not like that. It's actually 1% jump. Okay, so I got 99 steps. Now, so this is the percentage, and this is the corresponding milliseconds, okay, timing after zero crossing delay. So as I said, true RMS here, that's what they are. Now, on the far left here, the NY D01, I plotted what their percentage is. Now theirs goes from 30, jumping with 1%, to 99, okay? But what I've worked out is their 30% is actually 2% of true RMS power, because their delay after zero crossing at 30% is 8.52. And I will show you later on the oscilloscope that that's what it is. So 50%, okay, which you would think 50 should be 5 milliseconds, they have 6.5 milliseconds at 50. So 50 on the display here gives out 6.5. Now 6.5, it's close to here to 6.64, right? So it's actually between the 6.64 and the 6.32, which is around 22%. So their 50% is actually 22% true RMS power. That's what actually will be delivered at that phase angle. Okay. So as you see here, 50% power should equal 5 milliseconds. Okay. And their closest to the 50% power is 65% power. So their 65% is actually more like 50%. Okay. And the 70% is more like 60%. The 75. Now, as you notice here, the more closer we go up, the more it starts becoming correct. The 75 is actually 70, around that mark. Their 80% is pretty much 80%. The true figure is 3.36 milliseconds, and their one is 3.46 milliseconds, okay? Their 85% is close to the 85, is 2.96, should be 3.01. So their one is a bit more than 85% now. Their 90%, okay, is slightly a bit more powerful than the original, than the true 90. Okay, so maybe it's more close to 91% is their 90%. Their 95%, okay, is a bit more powerful, right, than the true 95%. So their 95% is more like 96% of true RMS. And their 99 is 1.54. So that is less than the true RMS 99, because true RMS should be 1.2 milliseconds. Okay, so their margin for the safety of the trike, they stopped at 1.54. My one goes up to 1.2. So my trike at 99 will more current will go through it. Okay. Well, my one goes lower than their minimum and goes higher than their maximum. Okay. So mine, I prefer my one. Okay. What I did, I reverse engineered the their circuit to create a circuit diagram. So this is the circuit diagram of the NY D01. Okay. I'll start at the bridge rectifier here. So they have 4 diodes in the back of the board upside underneath. That's the 4 diodes for the full bridge rectifier. Okay, so here we'll have the pulses of the wave, the negative and the positive. Okay, and which will give you actually 100 hertz in total. Having the negative and the positive wave being converted to DC, but it's not smoothed out yet because it's after this diode. Okay, so they put a diode here not to smooth out this output here going to the zero crossing pickup reference. So they put a diode there, and also they put a diode here just to isolate these circuits from each other. This one goes and gets smoothed out. It feeds the voltage regulator that they used, an adjustable one, and an LM317. And with these resistors in this configuration here, you will get a 5.1 volt output, which controls the circuitry. Coming back to zero crossing, this is a typical with an opto oscillator here, except they inverted. Normally, you will have a ground connection here instead of VCC. But because they're using a Schmidt trigger here, okay, inverter, they inverted the signal here because it's going to get inverted back again. So I think that's why they have done that configuration. And also the Schmidt or Schmidt trigger, I'm not sure how you pronounce that, but it does 2 things here. One is that they are isolating the inputs to the microcontroller, which they use the STC8H1K08. And from some of the voltages that might cause this chip to get damaged. Okay, so most inputs go through the inverter here, but obviously there are potentiometers that can change the values of the cycles and the power is directly to the chip because they're using the analog to digital converters on the microchip, and that's the pot configuration there. They've done a lot of capacitors here, probably to smooth out any EMI and from the transformer back EMF noise. Try to filter that as much as possible. Okay. But also the Schmidt trigger, it actually gets rid of a lot of switch bounce from switches. Okay. And conditions the your input. Any noise will get filtered out, and you get a better output, sharper output on the output, okay? The only difference is it's actually inverted. So if you have a high on this input, this will be a low. If you have a low here, this will be a high. So then the output as well for the driver here, which is the triac driver, they used an MOC 3021. Okay, that also is isolated from the microchip. It goes through the inverter here. So their output comes out from this chip, from this pin. This is the gate output. Goes in the inverter, comes out the inverter, so it gets inverted, and then back again to another inverter, and then out. So they are re-inverting the output to be corresponding to this. Okay, so it's put in twice, and then it actually switches on. So it switches on the low, yeah. So when it's a high here, it's a low here. So the output is inverted out of the chip here. And the input to the triac driver is run by the 5.1 or 5 volts, okay, through this LED here in series with it, LED 4, which is red, and in series with the internal LED of the opto isolator triac, and the ground is switched through the inverter. And then they have the output here, the triac output to run the gate, and that's how they've wired it. And they have a snubber here, circuit, a 39 ohm resistor in series with a 10 nanofarad capacitor, and they use the 1250 volts. And the MOV, I added that, so that's not part of the circuit. I've put that in. Okay, there's an extra protection of the triac. In my circuit, I actually added a LCD screen, alphanumeric, just 2x16. And they use, so this chip has a lot of pins not used, so I'm going to have to solder an extra 3 wires here at least. 2 is for the screen, data and clock, and 1 is for a switch that I've made to have double pulse. And so I've got a 10K pull-up here. Of course, this chip has pull-ups as well, but in this case, I think it's better to have an external pull-up just to try to condition this input before it goes in for any back EMI and all this noise from the transformer when it's welding. And what else? And then they have a status 0 crossing LED here. So the second LED over here, okay, if the 0 crossing is not working, that will not light up. So I called it status 0 crossing because I think it also, I'm not sure how they done it in the software, but it's supposed to be an indication if the microcontroller is working, okay? But if you take off the 0 crossing input here, so that's the output from the opto here, and goes to the input, and it goes there in the green to read the 0 crossing, okay? And the first LED is only just to indicate you have power because it's only hooked up to the VCC and ground through this resistor here. And yeah. And then they have a TM1650 chip running the LED display. And that is also the programming pins on the chip. So that's pretty much the circuit. And of course, what you're seeing here is the extra pins that I'm going to be using. Now, I could also, the zero crossing LED is the only one that's running directly on the chip, okay? Direct output or input through the chip. The reason why I called it input, because it's actually switching the LED to ground, because this has got VCC. So it's switching low here, push-pull configuration. So it's actually really an output, but I called it an input because the LED is inputting voltage into it, and this is syncing it to ground. For that reason, what else can I tell you? Yes, so I wanted also a fan output to be able to have the fan on a timer. So I don't want the fans running all the time. So every time I press the push button here and do a weld, you can see there, okay, it's welding, supposed to, switch the triac on. I want the fan to come on. And also when I was doing the software, I thought, if I'm welding at low current, then the fan doesn't have to go for so long, right? And if I'm going to weld at high current and a longer time, then I want the fan to go on for longer when it switches on. So I could use the same pin that this LED is hooked up, and that would save me soldering anything around the chip, because I could disconnect the LED, this one here, the red one, and hook the input where the LED is, which is, let's say, the output of the chip here. And I can connect a fan, a transistor there, or a MOSFET to switch on a fan, okay? Or I could use any of these pins that are not used. The only problem is that the chip is so small, the profile of it, these pins are very close together, so it would be a bit challenging to solder the wires. But to run, if I want the LCD screen, okay, then I would have to solder anyway on it, because you can use any of these pins, of course. I can change it through the software. And I will show you my one when I press the switch, which is the pulse, okay, output. I will show you on the oscilloscope here, which I have hooked up. So when I press the switch, there is my pulse, okay? And if I press the switch at the same time, you can see there's one as well. So let me change the time to be the same as this, 200. Okay. And I will show you now that my one, it's set at 1% there. Okay. So if I move the cursor and measure when mine fires, it's firing at 8.9. Okay. Or 8.88, roughly. And that's my 1%. And if you can see it here, 1% is 8.85 milliseconds. Okay. Now, depending where the cursor is, if I got it exactly right there. Okay. That's where mine is. Now, I'll show you the 50. Okay. And I'll show you the true 50. So I'll change, wrong pot. I go to 50%, 50% on mine, and they have theirs 50%. Press the button, both buttons. Now let me focus in the oscilloscope to be able to see what I want to show. So in the green, okay, is the actual zero crossing switching, okay? And the yellow trace is the output from my circuit, and the red trace is the output of the NY D01 circuit, okay? Now, let's do it again. Press the button. Okay. So let's measure the 50%. That's the zero crossing point, and it fires when it goes low. And there, I pretty much can around there, okay. 6 point, okay, 6.63 milliseconds. Okay. You see here 6.63. Now if we go to the chart, on the chart here, the 50 is 6.5, okay? If I change the scale here, you can see it's not exactly right now because to get more accuracy. So if you want the oscilloscope more accurate, you need to expand it as big as you can. Okay. And you can see here, 6.49, 6.4, 6.5, okay? That's when there's fires. And you can see on the chart, 50%, 6.5. That's when there's fires, 6.5, you can see it there, 6.49. Now, my 50%, so that's just to show, mine is showing 50%, and I'm going to fire, where's the button? Okay, the button there, watch the scope. And now we'll zoom on mine, zero crossing, okay, point. We're going to measure the distance between when mine fires, which is there. It's fired there. And we'll go down to here. Okay. And you can see there, 5.01, 5 milliseconds, okay? Now, depending if your cursor is slightly not 100%, in actual fact, look at, yeah, I move it 1 point, it's 4.99, one little bit, it changed it to 5.01. So it's spot on, 50%. Now let's try, let's go to 25, okay, for example. 25%. We'll press the button, okay, and we'll see what it will read. Okay, now it's fired over here. roughly there I've got 6.31. We'll go to the chart. I said 25%, yes, 25%. On the chart, 25% is 6.32, and mine says, the oscilloscope says 6.31. Okay, spot on. That is spot on. So, sorry, I keep changing the wrong pot. It's this pot I got to change. Let's go to whatever, right? 70%. Okay. Fire the button. Weld. See what that says. $3.97. That's showing 3.97. We'll go to the chart. 70%, 3.96. Okay. Spot on. 3.96. That's what the chart says. So that's the true RMS of 70% power. What else can we change? That's the pot, yeah? No, always the wrong pot. It's this one. We go to 75. I want to jump by 5 because that's how my chart is. Okay. 75, press the button. Okay. Just want to show that I'm not cheating, because I'm not. Okay, let's see what 75% is. This is saying 3.69. Let's see if I have it right there. 3.65, okay? We go to the chart, 75, 3.68. But let's see. There's probably more. 3.67. Okay, and it should be 3.68. Spot on again. So, what else can we go? We'll go 85. Okay. Come on. Of course, maybe this again is the reason why they went from 30 to 99, to have more wider control on the pot. Okay, fire the button. We'll measure the 85. I say it's around there. It's saying 3.03 milliseconds. Let's check the chart. 3.01. Okay, so 85 should be 3.01. And again, let's expand this. No, because now it's not reading the zero, the other. I cannot. .04 should be 3.01. There you go. So yes, so my scaling is according to true RMS. Okay. Now let's also show you there one. Zoom out of this. If I change this to 30, what did I show that? And press the button. I gotta press mine to work, and measure the 30. So that 30, I think I did show it. This, yes, is 8.54. Okay. or 8.52 there. And according to the chart, there 30 is that. Okay, I think I did show this, sorry. Repeating myself here. So that's about it. So when I'm finished with the software, okay, I will decide to how I'm going to have this configuration. Oh yeah, sorry. And the other part I haven't showed, if I disconnect their display, okay, and I'll do it all live here. That's running off the NY D01, okay. We'll disconnect that and I'll plug this in to my circuit just to show you that mine does run this at the same time. Okay. And you can see there. So when I vary, if this phone can focus, no, it's not focusing now. Okay. So you can see there, 99%. Okay. It's running both display. So if I don't want to run the LCD, I still can have that same. Once I load the software into the chip here, there's the chip there. Right, one cycle, 20 milliseconds. Okay, 30 cycles, 600 milliseconds. So you can see that running, and again, 99%, 73. I kept that the same, okay? Whatever it shows here, it's showing there. And also, I haven't showed another thing, sorry. I'm cutting myself short here. The other part that I did with my software of running the same chip, I've done a dual pulse. And I haven't shown you the fan timing. So when I press the button, there's my fan output. Okay. So that will time out according to how much power you have set. So if I set 1%, then when I press the button, it's not going to take as long on. So that's imagine that's your fan. See, it's a shorter time for the weld. If I change the high percentage, then there's going to be a longer delay. So it's worked out on a ratio on the how much power will equal to longer delay according to higher power, longer delay for the fan. Okay. Also, what I did, I've got this wire here, is the switch for the double pulse. Because on the circuit diagram, I'm not sure if I explained, but I've got the double pulse here. It gives out a double pulse. So if you switch this on, okay, the LCD screen there, can I just leave this? Okay. Once I switch that, now it's 2 pulses instead of 1 pulse, okay? Now on the double pulse, quickly I show you here. When I press the button, of course it's got a long delay time. Let's cut the delay down. 1 cycle, okay? There is my double pulse. So I'll move the cursor out of the way. 1 cycle. If I do 2 cycles, there's the 2 cycles and the double pulse. The first pulse with a half a second, 500 milliseconds break in between, roughly. Actually, that's a bit less because I've set the power to, oh no, sorry, I'm 47% here, 40% power. So the time gap here, let's measure that, between the first pulse. Okay, that's at 25 milliseconds, okay? If I go down with my power, okay, let's say 2% power. Now, the gap time is smaller. Okay, it's done on a ratio configuration as well. Now I have 17 milliseconds between the first pulse and the second pulse. So that's a full pulse, negative and positive, okay? And there's your 2 cycle, okay, pulses. And the more power I put, okay, let's say 92% power, and I press the weld. Now the time between the first pulse and the other ones, now it increases to 50 milliseconds, okay? So the way I've worked this out, okay, I used information on the net regarding what gives a good time between the first pulse and the second pulse, okay? So I got that information from Google AI. So that's where I got that info from. And you can see at 92% power, the triac is fires early, as you can see there. Okay, positive and negative waves. So that's the dual pulse configuration, and it's not set by my controls. It's set internally and automatically. So the fan again increases by the fan time increases by how much power, and the gap time increases. Now, when you do more cycles, okay, so I increase the cycles here. So now I've set, let's say, 500 milliseconds, okay, half a second. I would have to do that now. Press the button to weld, and the cycles increases on the first pulse as well. So now I've got 2 cycles running there, okay. You can see 4 pulses, which equals 2 cycles, and then a gap, and then your main weld cycles. And you see the power is different. You can see the power of the first pulse is much smaller, which is about 20% power. Let's say that's 100%, 99%, and that's 20%, something like that. So it's done automatically in the software that I did, okay. So that's the other part that I didn't show you, but that's how it is. So that's my weld. Oh, one more thing. If I go back to the first pulse, so I just switch it off. Now it's 1 pulse. The other thing that I did, originally the NY D01 circuit, okay, if you increase the cycles, that's the maximum, is 1 second, 50 cycles. And you can see, press the button, weld time, it's 1 second long. If you press the way they have it, this is imagine a foot switch, 2 times, 1, 2, it will give you 2 welds, okay. The maximum it goes is 2 welds, right? If I press it 3 times, 1, 2, 3, really quickly, it still gives you 2 welds, okay. I'm not sure if people are aware of that, but yeah, that's the other part that it does. I've made mine, okay. If I press the button 2 times, okay, 1, 2, it gives you 2 weld, right? But I've made the cycles there. When you press the button here, it shows me how many times I pressed the pedal. So press it once, 1, and there's your weld. If I press it 2 times, actually 3 times there, it counts how many times. But I've made it a maximum of 4 times, okay? Yeah, because I don't want to be counting any more than 4. But yeah, so I've made once, then you release, okay? If you count, press it 5 times, you let go, it will zero out. So it will not weld those 5 times once you release the switch. If you hold it down, it will weld. Same as the original one, NY D01. If I press it 2 times, it does 2 welds, okay? If you press it 2 times and let go, it will only weld just the 1 weld. Same with this. If I press it many times and let go, it's only going to do 1 weld. You see? But my one shows you how many times you press the pedal, okay? And while it's welding, it's counting down your welds, okay? Yeah, and you can see there, it's the oscilloscope, okay, is showing the welds. So that's the other part that I did. Yeah, okay.